Hopefully nobody else is running into the issue I am on Meetup, but if they are, we'll at least have it recorded so they can join or watch it later. I'll go ahead and introduce our topic today is building high throughput, event-driven, multi-tenant platforms in the cloud, presented by Josh, and he's a principal engineer at Zscaler, where he's a founding architect for the ZPC platform and a leader on the platform engineering team. With that, I will hand it over to you, Josh.
Awesome. Well, thanks for having me, Alec. I appreciate the opportunity to come in and talk with you folks. Ironically, it's been a long time since I've been to Kansas City. I was actually stationed at Whiteman Air Force Base a long time ago in the early 90s. But I remember I really enjoyed Kansas City. Maybe I'll have a chance to make it down there again at some point in time. Anyway, let me go ahead and share off my screen. Let's go ahead and share off the entire screen here, and let's get back to where we were looking at. So I'll get the boring stuff done with here. As you may have heard at the beginning of the call here, I'm out here in Seattle, Washington, newly out here in Seattle area as of about a month ago. So just relocated from Raleigh, North Carolina. But I've been in this industry for over 20 years now. So I've seen a lot of things and been through a lot of the different phases of the industry. I'm also Microsoft MVP on the Azure side. And as Alec mentioned, my day job, I'm a principal software engineer at Zscaler. So I'll actually mention a few of the things because some of the concepts that we're going to be talking about today were actually implemented as part of our platform at Zscaler as well. And I've used them previously to that. So some hard fought lessons that I'll be sharing a little bit along the way. Feel free to reach out to me on Twitter, or I guess they call it now X. I have open DMs, so feel free to reach out to me. And I have a website and an email. So I'll present these at the end if you want to have some other ways of getting a hold of me and talking with me. Before we kind of jump into some of the details around some of the solutions I'll be proposing is we want to kind of a quick context here of what is multi-tenancy. So this is your pretty standard definition of multi-tenancy, which is an architecture in which a single instance of software applications and its infrastructure serves multiple customers. In modern terminology, we're also talking in the world of SaaS here, right? Software as a service. But multi-tenancy has actually been around for quite a long time, actually since the early days, right? Back in the mainframes were actually all multi-tenancy back in the 70s, 80s, 90s. And we started kind of really having some of the more modern concept of multi-tenancy started to get introduced as virtual machines became a thing, in the 2000s. And obviously today, we have a lot of multi-tenancy conversations, around Kubernetes. And we'll be talking a little bit about Kubernetes today, but as that's the platform of choice for kind of deployment of multi-tenancy and kind of SaaS-based apps today. But it won't kind of be exclusive to Kubernetes. We'll happen to use that today, but obviously your mileage may vary. You can still go traditional VMs. And worked with a few customers not too long ago that were running JavaScript on IBM mainframes. So, there's a lot of interesting things going on out there. But that's multi-tenancy. But really, what are the challenges around multi-tenancy? And by the way, I neglected to mention this at the beginning, but this is a nice small group here, so feel free to chime in with questions. Or maybe Alec, if someone drops a message on there, you could shout it out to me. Don't mind interruptions. Don't mind going kind of different routes with the conversation. So definitely feel free to chime in. But what are some of these kind of real challenges really around multi-tenancy? Because it's not easy, right? And it's not easy, and it's even harder to get right. And even when you get it right. I'm getting a little echo there. Is someone? Oh,
should be good.
Good. Okay, great, thanks. And even when you're right, you have to make compromises. So what are some of the complexities with this, right? Well, distributed apps today are inherently complex themselves, right? So as soon as you're talking about any distributed app, especially event-driven, right? You're automatically talking about complexity, right? You have multiple services talking to each other. You have multiple APIs. You have typical microservice deployment. So we have a lot of complexity in general. And then when you add the multi-tenancy layer on top of it, that complexity becomes exponential, right? In particular with multi-tenancy, you have to deal a lot with noisy neighbors and understand how you can kind of isolate bad neighbors from good neighbors or just busy neighbors and loud neighbors from not loud neighbors, right? So that we don't interrupt each other. We don't drive each other crazy. So noisy neighbor is a is in particular a big challenge with multi-tenancy. Also, data isolation becomes much more important, right? No customer, we don't want one customer A seeing another customer's data, right? And so data isolation becomes really, really important. We don't want any data leaking from one customer to another. And also throughput management, scale becomes a big issue, right? It's a little bit related to noisy neighbors, but at the end of the day, throughput management becomes tricky. Because once again, you have, as opposed to a traditional app that may just be serving a single customer base in a corporate, you have lots of different types of customers who have different types of behaviors and characteristics. And so optimizing their experience and at the end of the day, their throughput becomes really tricky. And at the end of the day, cost, right? Cost optimization. And if you're selling a product like on software as a service, improving those margins, right? So ironically, the challenges that come with having a really well-tuned multi-tenancy environment are competing challenges, right? You want to give the best experience to the customers. Customers have a high expectations of what that experience should be, right? Whether they're small or big, they want things to perform well, right? And that goes against having a cost-effective environment, right? And actually making money off of your product, right? And improving your margins, right? So there's a lot of competing challenges when it comes to this. And there's lots of different ways that you can address these challenges. So I'm going to give a rather relatively opinionated way of being able to address some of these challenges using some various ingredients to a recipe. And it's a recipe that I found has worked successful. Obviously, as with many things in the software world, and architecture in general is always compromises, right? And so we'll talk about some of these compromises. There's never a silver bullet to kind of get everything you want. And so it's all about compromise. But what I have found over time is that some of these ingredients have really helped me on my journey of building good multi-tenant platforms. So one of the first ingredients is we want to reduce complexity. So how can we reduce some of the complexity? Well, we're going to introduce you a little bit to Dapr, which is the distributed application runtime. And we're going to use that as our foundational framework for building some of these complex platforms in the effort to reduce some of the inherent complexity that comes with this. We also want to reduce some of the noisy neighbor issues. And we also want to be able to effectively manage throughput. When I say manage, sometimes it means more throughput, but sometimes we want to throttle people. Sometimes we don't want to give people as much throughput. Maybe they're a free customer, right? Or whatever, or a dedicated tier, different tiers and apps. But so we want to be able to effectively manage throughput. And I'm going to show you a little bit how we can use Kata to kind of reduce the occurrences of noisy neighbors and manage some of that throughput. And in our case, I'm going to make use of EventHubs as our eventing platform. It's a great choice for some of the scenarios that we'll be talking about, but you could honestly replace EventHubs with Kafka, which is what I mostly do in my day job these days, working with Kafka. And ironically, EventHubs is not Kafka, but you can talk to it at a protocol level with Kafka, so it can behave like Kafka. But you could also apply these things to things like Service Bus and RabbitMQ. So a lot of these concepts are pretty portable. We'll also talk about how we can use CosmosDB for better data isolation and manage throughput, one of my favorite data platforms. And we'll use that as part of the recipe. And finally, we'll kind of combine it all together with helping manage another type of complexity, which is our deployment complexity. Multi-tenant platforms get very, very, very complex when we're talking deployments. And so we want to make sure that we can manage that complexity as well. So we'll be using a CNCF project called Flux to help manage that complexity when it comes to deployments. And along the way, as we're kind of cooking up our meal here, we want to keep it healthy. So as I say, hold the salt, right? But in this case, the dollar signs, because at the end of the day, we need to do all of this in a cost-effective way. And that becomes really, really tricky. You can do all of this very well in an expensive way, but we want to do this in a cost-effective way. And so we'll talk about some of the compromises around cost and how we can kind of save on cost as well. So let's go ahead and just kind of dive right in. And by the way, once again, if there's any questions along the way, please go ahead and just shout out and chime in. So let's talk a little bit about reducing the complexity with Dapr. So If you haven't heard of Dapr, Dapr is the distributed application runtime. It is essentially a set of building blocks for building microservices. And they're building blocks done in a really very kind of ingenious way. So these building blocks come in the form of common things that you need when you're building microservices: state management, pub/sub, observability, working with secrets, working with configuration. There's actually a bunch of other building blocks that aren't updated here on my latest graph here. Workflows, all those kind of things. All of these building blocks that most modern distributed applications need. And these building blocks provide a layer of abstraction to make working with the underlying providers of these building blocks a lot easier to work with, and also give you a great deal of flexibility. Flexibility in the form of, hey, I want to run different backends in local dev, or different platforms in local dev, maybe versus dev environments versus prod. Because we all know, cloud is expensive, right? And sometimes you want to run different things, but I don't want to have to, recode and retool something. Or maybe, and this is often the case, you have a new platform, you learn things. You learn that, hey, maybe EventHubs isn't the best solution for my eventing. Maybe the particular patterns that I'm seeing more lend themselves to something else. Or maybe I want to, bring it on-prem, right? That type of flexibility is provided by Dapr, and it kind of encodes common best practices. So it makes it easier for you not to step on your own feet, right? You have to work a little bit harder to do it wrong. And the nice thing about this is it really is code cloud agnostic, right? I'll show you some examples of some of that. I'll show you some examples here in .NET today, but I actually use Dapr in my day job in Go. But there's lots of other frameworks available. At the end of the day, if you have some code, I should say SDKs available, but at the end of the day, you don't even need an SDK. If you have some code that can make an HTTP call or a gRPC call, you can work with Dapr, because Dapr is actually implemented as at least in the Kubernetes world, as a sidecar. So this is actually a process that lives alongside of your services, that provides all of these features and functionality, and it's all API based. The nice thing is the SDKs for common languages are available, and it makes it really, really seamless and really easy to work with. But at the end of the day, if you're in some interesting environment, if you can make an HTTP call or you can make a gRPC call, you can work with Dapr. In today's demos and in today's kind of code walkthroughs, we're going to actually be using some of the CosmosDB providers for state management, and for pub/sub we'll use EventHubs. But at the end of the day, and you'll see here in a minute, we could swap these out for Kafka. I could swap it out for Service Bus. I could swap it out for, RabbitMQ, various other pieces. I could change it from CosmosD to Postgres. So there's a lot of different flexibility. There's also a lot of things I'm not going to get into some detail on. Obviously, this recipe involves a lot of ingredients, so we can kind of we'll be able to kind of cover the high level of those. But I definitely encourage you to spend some time, if you like any of these particular ingredients, and kind of dig into it a little bit. And I'll give you some resources at the end of the call to kind of be able to do that. And finally, like I said, really from a Dapr standpoint, and really most of this presentation, we're going to be focused on Azure. We're going to be using Azure solutions. They're obviously the best of breed for a lot of use cases. But if you're in an AWS world, or you're in a Google Cloud world, or you're on-prem, a lot of the concepts that I'm going to be presenting here could absolutely apply in those particular cases. Like, for example, it's worth mentioning, in my day job, I spend a lot of time on AWS and Azure, right? So this is fairly portable concepts. So let's dig in a little bit more about working with Dapr. So I'm going to present here a little bit of a smaller use case, pretty simplistic. Obviously, distributed apps have typically a lot of services and a lot of things coordinating, but we'll kind of keep things simple a little bit. In this particular case, we have a order request coming in through an API, right? And we're going to interact with Dapr to help us both talk to Cosmos via in a generic way, to work with our state store component, and also with working with EventHubs, so using a pub/sub component. And all of these things will be funneled through these Dapr sidecar pieces here, and then obviously land in order processing. I'm not going to have time to get into some of the more details and some of the other options, but it's worth mentioning that along the way, you get a lot of free stuff with Dapr without even having to do anything special. some of that free stuff is some of the visibility pieces. So those distributed traces that are also helpful when we're building distributed apps are automatically provided by the underlying framework. So and those can be fed through OpenTelemetry, which is kind of a standard now for working with distributed traces. But we could actually visualize them and feed them into things like App Insights, or if you're in a different kind of shop, you could do Jaeger. There's a lot of different places that you could feed them into, but some of that plumbing comes for free, and I definitely encourage folks to kind of dig into that a little bit. But let's see what this looks like a little bit in action from the standpoint of what your code looks like, right? So what we have here, and by the way, I'll make this project available up on GitHub here. I'll share out something afterwards. This hasn't been published to GitHub, but I intend to do that probably today or tomorrow. So what we have here today is an order API and an order processing service. Now, Dapr has, you can do local development with Dapr. There is a local runtime. It's actually pretty easy to download that runtime and essentially do a Dapr init, and it'll create you some Docker images behind the scenes in here. So local development experience is actually pretty good with Dapr. The other nice thing with Dapr is that I may not, in local development, want to work with EventHubs yet. I may not be ready to work with EventHubs. I don't want to pay to have EventHubs spun up or CosmosDB spun up. Because there's a nice layer of abstraction, I can actually just use Redis instead of using CosmosDB for my local development, right? And my code doesn't look any different. What changes are these components. So Dapr has components defined. Those components allow the Dapr runtime to understand what are the downstream platforms you actually want to work with. So in this particular case, for this example, we have a couple different components. Now, these components are defined in YAML. And so this look, for those familiar with Kubernetes, this looks very Kubernetes-ish because it is. I'll talk about it momentarily, but Dapr actually gets deployed to Kubernetes environment as well, and it deploys CRDs. Dapr does not require Kubernetes. People actually run it on VMs, and that's not necessary to have Kubernetes, but that's where most folks end up deploying Dapr to. But at the end of the day, we define these various components. In this particular case, I've defined that I have a component called order pub/sub, and the type, though, is EventHubs. So in this particular case, I could use Kafka. I could use whatever I may want, and you can go to the Dapr site and you can find out the listing of all the supported things. But at the end of the day, you define a particular type, and then you provide some metadata. These are things like the connection string that I want to work with in this particular case, and this metadata is very much typically associated with specifics around that particular platform. So the metadata will be a little bit different depending on what type of component you're working with. But essentially, I give it all the information that it needs. And if you recall, I was mentioning that sidecar. That sidecar is actually hosting and loads up all these configurations, so it knows how to interact with it. We have a couple for state store as well. For example, this is and this database doesn't even exist anymore, so I'm not worried about master key leaking. But this is a component that's defined, and this is the state store, and I'm using Azure CosmosDB. So these are the definitions for the components, and I can have different definitions for different environments. I could have one for dev, a different one for prod. I could have a different one for local. As long as I have the component name is defined, that's all that Dapr needs to work with. But if I go, for example, over here to, and I'll just show as an example here, I'll just cherry pick a couple of the services out here. So we have this order processing service. So the order API, as you might recall from the picture, kind of sends things over to EventHubs, and then and then listens for that. So in our project here, we actually have a reference to the Dapr client here. And the Dapr ASP.NET Core client here. This is the SDK. This is actually kind of taking care of all those HTTP calls and gRPC calls behind the scenes for us, depending on what our configuration is. And then in our code itself, this is where you start better understanding some of the reduced complexity here is. If anybody's ever dealt with event kind of based processing, you know there's a lot of plumbing to work with, right? You have a lot of things that you need to do at an SDK level or code level to be able to kind of handle those. As opposed to having to handle all of those, at the end of the day, and this is the .NET implementation, obviously there's some slight variations for Go or Python or whatever it may be. At the end of the day, we have a function that processes an order, and we have a attribute. And this attribute basically is a Dapr attribute, and it says, hey, this is that component that we defined. If you remember, we defined that component up here, order pub sub. So this is the component that we defined. And hey, I want to listen on this event hub, or in Kafka speak, topic. And so this is essentially saying whenever anything comes in to this topic, please trigger this. And it's as simple as I'm pulling out an order model. In this case, I'm using JSON, and I have a reference to the Dapr client. And so this is using dependency injection to give me my Dapr client, and it's automatically taking care of all the details of how to deserialize and serialize things, right? And all I'm doing is I've received that message, and I'm updating the status. And now I am going in and making a call to save state. So for me, saving the results of the Dapr order, and obviously this is pretty simplistically contrived, right? But imagine that there's some more interesting things going on here. But now that I've processed them, I've gone in here and taken on the order state. I've taken on it and gone and saved this to Cosmos. Or in this case, since I'm running locally, it's actually configured for Redis. So it'll actually save it to Redis. So in essentially one line of code and a few lines of code, I've listened to an event, and I've gone ahead and saved that to the Cosmos database. So this is just kind of a very lightweight example of what that experience might look like. Definitely encourage folks, once again, to spend a little bit more time with this and explore it a little bit more. But let's go ahead and kind of continue on a little bit with our recipe. And by the way, can you hear me okay? I'm getting a little bit of lag. Alec, can you hear me okay?
Yeah. Sounded good on my end.
Okay, great. Okay, just wanted to make sure. I got a little bit of a lag warning. Just wanted to make sure I was coming through okay. Okay. So let's go on to kind of what the next piece is. So we just kind of covered that initial reducing complexity with using Dapr. Let's talk a little bit more about how we can kind of deal with processing our events. So one of the challenges we have, and this is one of the tricky ones that we have with processing events, is you may have multiple customers coming in here, and they're passing in, let's just make up a number, 500 requests here, right? And that request comes in the order of JSON and actually gets sent over to some sort of order processing. And this looks fairly straightforward. And in most apps that aren't multi-tenant, this is a pretty easy problem to solve, right? We know how to scale kind of these things coming in. And just to be clear on things, when we're talking about most messaging platforms, and especially EventHubs, there is some sort of measurement of throughput, right? In the particular case of Azure EventHubs, throughput is defined by partitions. So when you spin up an Azure EventHub, you actually specify upwards of 1 to 32 partitions, 32 being the max default. You can actually call up Azure and get more if you need that. But this is actually your throughput, right? This is what your capable throughput is. Now, yes, you could always give it max partitions all the time, thinking, hey, this is easy. I just max it out all the time and I'll have all the throughput I need. But data can come into all of those given partitions, and you're responsible for reading data from that partition. So handling all the details of making sure that you're processing all of that partition data becomes a little bit more complex. Less so if you're using Dapr, but there's still some complexity there. But what gets especially tricky is that by default, if let's say that goes up to 500,000, right? By default, what ends up happening is that data gets spread evenly across those partitions, right? And so once again, still kind of okay. We're in an okay territory here. Okay, sure, it's being split across partitions, so it's kind of being round robin by default. I'm not going to get into some details of some other options, but there are other options. But by default, it's going to round robin across all those partitions. But what starts happening when you have 10,000 coming in from one customer, and then you have 500,000 coming in from one, and then you have a big customer sending in 6 million events, right? this is where you start running into a lot of the challenges around noisy neighbors, because you don't have a lot of control, right, over the throughput here, where that data goes to, which one might be the processed. Generally speaking, the loudest neighbor is going to be processed first, right? And this small neighbor is going to be processed afterwards, just the law of numbers, right? And then you also, what happens when, you know, that 6 million come in and I'm capped out on partitions, right? Hey, I can only have so many partitions. If partitions are unit of throughput, I'm going to start hitting some walls pretty quickly. So, you know, so how do we handle this, right? How do we handle when we have these noisy neighbors and we want to right size our workloads, make sure that, you know, the 6 million customer gets the throughput they need, the 10,000 event customer doesn't get trampled by the 6 million event customer, and how do we do this without having crazy high costs, right? By just dedicating a ton of stuff to, you know, a ton of infrastructure, right, to these customers. Well, one of the things that we can do is for managing kind of throughput noisy neighbors is using a combination of changing how we deploy our event hubs and using CADA. So one of the things that, and by the way, this is probably one of the more opinionated aspects of this. There are a lot of different ways you can slice and dice this. This is probably a good approach when you have that scenario that I was just talking about, when you have just lots and lots of, you need high volume, but you have lots and lots of customers with different volumes. And you kind of want to be able to right size things, right? This approach is not probably the best of approaches for if you have small volume, or if it's more of like an internal workflow process, right? So this is for event processing at scale, right? So one of the first things that we can do is start to partition our event hub and really our messaging platform in a little bit more broader terms than just individual partitions within a given event hub. So in this particular case, we have provisioned a event hub. We have provisioned a topic rather specifically for a given customer, Acme, right? And so Acme now has their own topic, right? And so when Acme has their own topic, we now can also have specific order processing services just for Acme, right? So this allows Acme to kind of scale independently of the other customers coming in. So we've to a certain extent dedicated some compute to Acme. The processing is now isolated. We can now also right size our partitions a bit, right? So we can say, hey, Acme is a bigger customer or is a smaller customer, they get 3 partitions. Contoso is a huge customer, they get 15 partitions. So we can start right sizing a little bit of our workloads and do some cost optimization as well. But the tenant throughput becomes optimized for a given customer, and it prevents those noisy neighbor scenarios. And we also give that customer a dedicated namespace in EventHubs. And that allows that customer to have essentially kind of its own pipelines, right? To be able to manage requests in. We've now fully avoided noisy neighbors in the case of the event processing. And we have right-sized the topic or event hub, depending on your nomenclature, for a given customer. Now, by default, though, you might start thinking to yourself, wow, there's a lot of compute there running for a customer, right? And that can become very expensive. Hey, that's going against your hey, thou shalt be cheap, right? Well, the way we address that is through CADA. So CADA is the Kubernetes event-driven autoscaler. So what CADA does for us, it allows us to scale Kubernetes in response to different types of events. So by default, you have something called a horizontal pod autoscaler, which comes out of the box with Kubernetes, that allows you to scale your workloads in Kubernetes, your pods, based on things like CPU pressure or memory pressure, right? So, you know, if your pods are running hot and they're 100% CPU, hey, spin up into one, right? Well, one of the things that CADA does for us is it allows us to scale based on other activity. So we can actually see, for example, how many messages are coming in. And based on how many messages are coming in and how fast we're processing those messages, scale based on that instead. And oh yeah, by the way, if there are no messages coming in, scale down to 0. So this is an introduction of a little bit of some of the attributes of serverless, right? So in the sense where if there are no messages being processing, you're not paying for it, right? So from a compute standpoint, so this allows us to have some of the isolation that we need, avoid noisy neighbors, right size some of our workloads, but also be able to scale to 0 on our compute side so that we're not incurring costs when there's no messages coming in. But there is no free lunch, as they say, right? So one of the challenges that we have with this approach that we'll be able to address towards the end of the talk here is that this does add some deployment challenges, both for our workloads in Kubernetes and for ensuring that all of these customer or tenant specific event hubs and namespaces and event hubs get created for us, right? And configured properly. So all of this depends on the ability to kind of have some way of deploying this in a uniform, effective way without adding too much complexity on this. So this is where architecture compromises happen, right? In order to achieve this, we're now having some more complexity that we need to address elsewhere. And once again, we'll address that a little bit later. And there are also some additional complexities when it comes to provisioning specifically event hubs. Event hubs has some optimizations that you need to make around how many namespaces you're allowed, how many event hubs within a namespace you're allowed. So there are careful considerations that need to take place that you need to be aware of beforehand, and you need to understand a little bit of like how many tenants I'm intending to have, or when I have this amount of tenants, this is what I'm going to do. Okay, what happens if I have this amount of tenants? What happens when I go from 1,000 tenants, from 100 tenants to 1,000 tenants, right? I have 1,000 customers on my environment. Well, you're going to have to make sure that you understand some of the various boundaries of event hubs or whatever platform you're using to understand what mechanism you need to make. Hey, do I need to create additional subscription? Do I need to call up Azure, for example, and say, hey, I need to be able to have, you have a soft limit on the number of namespaces right now in a subscription. Can you increase that soft limit to the hard limit? Things like that. You'll need to have some careful consideration. But overall, this approach allows you to have a great deal of flexibility with event hubs and Kata. Now, what does this look like though from a deployment perspective, or how do you get this stuff up and running? What does event hubs end up looking like a little bit? Well, what it looks like a little bit is, if we switch gears over here, is from a Kubernetes standpoint, we have various deployments that go to Kubernetes where we need to install Kata. Now, Kata is pretty easy to install. In this particular case, this is an example of installing a Helm chart that installs Kata. Kata will install all the CRDs and some controllers in Kata that manage all the kind of the plumbing that Kata needs. So it's fairly straightforward to get Kata up and running within a Kubernetes cluster. And this is beyond the scope of this conversation. There are some considerations at scale. We actually use Kata in my day job for thousands and thousands of services. So it will scale, but there are some considerations when you're doing Kata at great scale. So I encourage folks to take a look at those. It can handle a lot of scale, but there are some things that you need to do to make sure that that Kata doesn't have problems on your cluster when you're talking thousands of services. But that's the Kata infrastructure. How do we actually kind of get the wiring up? Well, luckily, your services don't need to have direct dependencies on Kata. When we deploy our services, your services know nothing about Kata. Kata is entirely abstracted away, but we still need to say, hey, this is my service. I'm using this topic and this connection, and Kata needs to be configured in the same way so that they match up. And how we do this is in our deployment, we deploy something called a scale object. A scaled object is a CRD deployed as part of Kata to the Kubernetes environment. And we essentially say, hey, I'm going to be scaling Acme order processing. So that's my service. So it knows the target of the scale. And oh, wait, I want to scale based on event hubs, right? And I also want to scale. And so how does it know what I need to talk to, right? Well, we have to give it some connection information. And so this way, the Kata plumbing deployed to the environment will actively query. So it actually goes back, if we go back to the diagram here, we'll actively query how fast are we processing? And what it does is it actually sends some signals to the existing horizontal pod autoscaler, which is the default behavior. It sends some metrics to there to get the underlying pods to scale in the way that that we want it to. This is actually pretty ingenious because Kata is actually not doing the scaling. It's using the plumbing already in Kubernetes to be able to do that. It's just feeding it custom metrics depending on how fast we're processing. So it asks those questions. How far behind am I getting? How many messages are there? And there's additional settings to be able to get it to scale as you want. And then from a, I'm sorry, was there a question or was that just coming off me? Someone coming off me? Okay, doesn't sound like there was a question, so that's fine. So what does this look like over on the EventHub side? Well, it kind of looks like this. So I spun up a couple EventHub namespaces for Acme for Contoso. So if we open up Acme, we have a dedicated EventHub namespace for Acme. And in this case, we have an orders EventHub or topic and Kafka names and Kafka names naming. And that's really about it. So each customer has their own namespace, and each customer has one or more topics in that namespace or event hubs in that namespace that handle whatever processing you may need, right? And so that's generally one approach to being able to handle effectively very high throughput scenarios, right? And avoiding noisy neighbors, but also avoiding some of the extra compute costs that would normally be associated. And some of this stuff has been more recently unlocked because of Kata. We couldn't effectively do this, or at least easily do this, prior to Kata coming into the equation. So this is a little bit of a newer approach, but we use this extensively in our platform, and it works very well for, once again, high throughput scenarios. So let's go ahead and continue on into how we handle the data side of the equation, right? The Cosmos database side, the data isolation. Before we can talk about, though, it's important to understand that there are some different strategies for protecting customer data, right? And about that, some different strategies for protecting customer data. And this really goes to, when you save something to a database, how do you save it, right? Well, there's typical row level partitioning, right? And what we mean by that is there's an extra column, right, in your database that says tenant ID, right? And that requires that every customer, every query going into here needs to make sure that it has that as part of the query, right? Saying, hey, select star from this where tenant equals this. And that is a valid approach. It gives you the ability to have very low cost, very high density, but it's also a little bit dangerous, right? You can have bugs that may leak data. Think about malformed query, right? And then next thing you know, you're showing someone's data for another customer, right? And your customers are not going to be really very happy about that. So although row level partitioning is a thing, and there are actually some strategies I'll talk about CosmosDB that minimize the impact of something like that. But it does cause some challenges, and it does mean that all your queries are going to be different for each customer. You need to understand what customer you're dealing with for every single query, right? There's also a middle ground. It's kind of container or schema partitioning. In CosmosDB world and a lot of NoSQL worlds, you have various containers, and you dedicate a container, and so that container has all of its own data, all the rows, right, in that, or documents in that particular container are owned by that tenant. And in the relational world, you can think of this as schemas, right? So you could have a given schema for a table in the relational world, right? So it's kind of container schema partitioning. And then obviously you have database partitioning, right? So everybody just gets their own database, right? And that's the highest level of partitioning, and it definitely works. But as you can see from below this little graph here is that the costs in isolation, right, are on the low side with row level partitioning. Database partitioning, you have very high isolation, which is good, right? Everybody's got their own database, but the cost is also very high, because one of the things with multi-tenancy, and especially with SaaS platforms, is you want to have some density. You want to have those shared costs, right? To be able to offset, right? And so database partitioning isn't the best approach to use in many use cases because it becomes very expensive. Now, you may have big customers who say, yeah, maybe you can give a premier or an enterprise tier, right, where they get their own database partitioning. Sure, but in general, though, for cost effectiveness on the platform, you kind of want to find a middle ground. The middle ground I'm going to talk about here today is really container partitioning, right? It's that balance between the dangers of row-level partitioning and the added coding complexity to row-level partitioning, and the expense, right, of database partitioning. And so why, this is one of the reasons why I'm a huge fan of Azure Cosmos Database. Azure Cosmos Database, there's a question. Alec, did you have a question?
Yeah, there's one in the chat. Can a relational database, i.e. SQL Server, be used in a similar high throughput application? And could you please compare and contrast these two scenarios and what use cases might be appropriate for each?
Sure. So in general, there's definitely discussions that need to be had when you're working with your own data modeling to say, hey, do I have a very fixed established schema, or do I have some more flexibility in my schema? Is it changing a lot? And that's, or is it highly relational, or is it not highly relational, right? So there's that first level questioning to say, okay, what is the appropriate type of data store for this, right? If you have highly relational data, and you're interested in minimizing the amount of duplicate data, the normalization procedures, right? Then you're generally going to kind of side towards the relational world. And by the way, I'm a huge fan of Postgres, for things like that, or Azure SQL, right? All of these will fit that bill. If you're on the NoSQL, if you're more on you need some flexible schema, maybe you add new properties a lot of times. There's a lot of variableness to the schema for your database. And generally speaking, this is no longer the case as much because relational databases have gotten really good. But generally speaking, NoSQL has historically had scaled better for high volume kind of scenarios. And I say that has balanced out a little bit because there are some incredible things being done in like Azure SQL and Postgres, things like that, for making traditional relational databases scale really well, which, they historically, it's been a challenge. It's, sharding relational databases is painful and things like that, but they're getting a lot better at it. So that leads me to the second part of the equation. So you need to answer that first question first. The second part of the equation, though, is whether you can use this approach, and the answer is absolutely yes. So I'll show you a little bit of the container side of the equation, but you can easily apply this to schemas as well, right? So you can have a schema and I haven't done this personally with multi-tenancy, but I've seen other products do this, and I've seen suggestions from guidance from Microsoft, and the same thing is that you have. If you're normally, like, for example, in Azure SQL, we have like DBO dot orders, right? You can have Acme dot orders, Contoso dot orders, so on and so forth. So you have that schema level isolation. And as soon as you have that schema level isolation, you can do some interesting things with security, with tenant specific credentials. And so I think they both can scale equally well. I think they both can handle multi-tenancy equally well, although I'm more of my experiences on the NoSQL side, and I do some Mongo stuff, things like that as well. But I think you can have success in equal. I think the best question is what does your data model look like? And that's probably the first one you have to answer. But after that, I think you can have success with both. Hopefully that answers your question. If you want to go into some more detail, definitely chime in there and chat, and I can go into some more detail on that. But with multi-tenancy and Cosmos database, one of the reasons I'm a big fan of this is it's almost like it was created for multi-tenancy. I swear it's almost like they were thinking of this use case in their mind when they were creating it, because it has the scale that you would want from any kind of database for a multi-tenant SaaS platform. But just as importantly, it has performance guarantees, right? Now, obviously, there's cost involved with performance guarantees, but if performance guarantees are super important to you, then you can say, no matter what, I don't care, make sure that this is never slow, right? Which is a kind of a little bit of a harder question to answer on the relational side. So maybe that's a consideration, but I know you can, but it's a little bit of a harder question to answer. But I want to guarantee this has to be. Once again, you're going to pay for that, right? But so the scale aspects of it is excellent, and those performance guarantees are what you would want, right? But there also it's hugely flexible in that partitioning and isolation strategy. So I'm suggesting some of the default places to go is really that container partitioning because it's a nice balance, right? But if you find that there are use cases for row level, or if you want dedicated, there is a fantastic spectrum within the Azure Cosmos database that gives you a ton of flexibility. And you can even do that within a single application. You can have certain customers going to some dedicated throughput, certain customers going to shared throughput. And now obviously row level requires some code changes, so that's a little bit of a different story. But technically it does a really good job at all of the above. So it's tremendously flexible. So even if you find that, hey, container partitioning isn't the right choice for me, or isn't always the right choice for me, you have other options as well. So, but at the container level, the isolation is pretty good, right? There is some shared provision capacity. So that's kind of a balance between, hey, I'm going to share some throughput across a given database, across these given containers, which it does max out. So there's some considerations. I think you can share capacity for up to 25 containers within a given database. And I can say, hey, or I can spin up a different database and I want a different model. I want dedicated capacity for a given container, right? So there's enough flexibility where you can kind of balance things out, right? You can say, hey, I want to have share capacity for these ones, but I want dedicated capacity because this is an enterprise plan for my product, right? So it gives a nice balance, right? It does also reduce the likelihood of data leaks, right? With tenant-specific credentials, right? You can do RBAC. You can actually even do resource tokens down to specific partition keys. This is one of the ways that kind of addresses some of the row level isolation down to specific partition keys, right? You can say, hey, this partition key is only available, so I can't query something without a partition key. And if your tenant ID is part of the partition key, then you have some options there. Partition key modeling is super, super, super important with the Azure Cosmos database, well beyond the conversation of this talk. But before you even touch this, make sure you really, really understand partition keys within Cosmos, because you will live and die in Cosmos based on your partitioning key and your partition key strategy. So make sure that's really important. But we also can reduce some of the potential for noisy neighbors, right? Because we do limit kind of the blast radius, because we would have multiple databases and containers in there. So the blast radius will be limited for noisy neighbors, or if you have very, very busy, maybe an enterprise customer, right? You can provision still in Cosmos database, provision them a dedicated container, give them their own capacity because they're paying extra for it, things like that. So it gives you a great deal of flexibility in how you manage your throughput guarantees, data isolation, security standpoint. But there, once again, and we'll cover this in the last few minutes of the talk here, we are now also, once again, just like EventHubs, adding some complexity, right? Because you have to consider things like, okay, I'm only allowed to have so many shared capacity containers per database. I'm only allowed to have so many containers across a CosmosDB account. I'm only going to have so many CosmosDB accounts across a subscription. So depending on how your environment grows and evolves, you may need to have some better understanding of, hey, this tenant's going to get deployed to this database, this tenant's going to get deployed to this database, because some of those restrictions are at place, right? There's always limits on any kind of SaaS, on any kind of platform, on any cloud, right? And so you need to take those into account. And also keep in mind is that some of the default limits are soft limits. If you're a big customer and you're really working at scale, you can call up Microsoft and say, hey, can you please up that to, something bigger? And a lot of times they will be able to do that. But, there are always hard limits though. So multi-tenancy is really, really great with Azure Cosmos database. And I suggest a good starting point is that container level partitioning. And so what that looks like here is, at the end of the day, is you will see a Cosmos database that looks a little bit something like this.
I do have a question for you while you pull
Yes,
that
please.
up. You said you will live and die by your partition keys in Cosmos. Do you have any recommendations or to get better at that, learn them well, not spend a fortune trying to learn them, any of that sort of thing?
Yeah, there's actually they have some really good, maybe I'll Google at the end here real quick. There are actually some really good documents from Microsoft on partition key modeling. But in general, partition keys will be your throughput, right? So you want high generally speaking, you want high cardinality in your partition keys. So you want a good level of, but not too high, but a good bit of cardinality in your partition keys, because the more separate kind of partition keys, it can scale out. If you put everything into a single partition key where most of your records are fall under a given partition key, you end up running into something called a hot partition, because it can't scale you out. It can't add more compute behind the scenes. You hit a wall. So in general, my recommendation is take a look at your, you want a good degree of cardinality with your partition keys, and also take a look at your the hierarchical partition keys. They're a recent introduction last year or so, year or two, and they also address some of the partition key modeling challenges where you're less painted into a corner with partition keys when you have a little bit of a hierarchy on them as well. That kind of got around some of the challenges and some of the things with partition keys, but I'll see if I can find a link to that at the end here to see if we can find a good article on that. But they know this is a challenge, and there's lots of good videos and articles on partition key management and modeling for that. Hopefully that was enough of an answer.
Yeah, for sure.
Too much detail. Okay. So in this particular case, for example, I have an Acme collection. A container, I'm sorry, with items just for Acme, and Aviato has items just for Aviato, and Contoso has items just for Contoso, right? I'm using the serverless platform here, so you can, you have some challenges with, I can't show you an example of how to set bandwidth. I'm sorry, throughput for a given one, because I'm on the serverless one, but you can actually, do some slicing and dicing of where you want to assign your throughput, and throughput comes as obviously cost, right? RUs in Cosmos. But with the last few minutes of the call here, I want to wrap this call by discussing a little bit of the deployment complexity. So this is kind of a common picture of what deployments for multi-tenant apps look like, right? You have microservices, you have messaging, you have infrastructure, you have all these different pieces. And now we've introduced even more complexity because we have tenant-specific microservices. We need to deploy tenant-specific namespaces and topics. We have tenant-specific containers in Cosmos, and so and it's not just once. You got to do it for dev, prod, stage. You may even have multiple stamps, multi-regions around the world. So complexity gets pretty significant, right? Working around some of the compromises that we've introduced to be able to satisfy some of the other needs that are important from the standpoint of noisy neighbors and costs and so on and so forth. So one of the tools that we use that I've had a great deal of success in for these specific scenarios is really around GitOps, and specifically Flux. So Flux is a GitOps tool set that allows you to essentially manage within a Git repository, manage the definitions of what your environment looks like. And you deploy Flux to your Kubernetes environment, similar to deploying Kata and Dapr. And Flux actually goes back to your Git repository and reconciles things. So your Git repository becomes your desired state. So if you have, for example, add a new service, well, you simply add it to your Git repository, and Flux, depending on the schedule that you set up for that given that given source of truth, will reconcile it, and it will say, oh, service C doesn't exist yet. I need to create that. And so it'll go ahead and deploy service C as defined in your Git repository, which is just YAML and your normal YAML Kubernetes stuff. It also makes sure that, hey, someone accidentally deletes service B. It will notice that service B got deleted, and service B is part of the source of truth, so it will re-spin up service B. So it also helps in reconciliation and drift, right? Accidentally deleting something. This is something that is a lot more challenging to do when you're using traditional push model deployment mechanisms, whether it be Azure DevOps or whatever tool set you want to use, GitHub Actions, where it's a kind of a one-time push. This does constant reconciliation. So if you delete something, it'll always make sure at a given interval, which is usually minutes, it will make sure that your Kubernetes environment matches the source of truth, right? And what this looks like in practice is, and I'm going to spin over here to my GitHub project here. And in practice, Flux is defined by a structure, right? The structure you see here is a structure I chose. You can actually have lots and lots of different structures, but what we have chosen to do is we define our clusters, and this is essentially says this is how Flux talks to and says, okay, where do I need to look to know what to reconcile, right? And in this particular case, I've defined some infrastructure and I've defined some tenants. And these are all customizations, and they point to where it should look for different pieces. And so one of the things that we wanted to do as part of our deployment, and this is kind of a best practice with Flux and really any other GitOps, is you kind of define your apps, you define your clusters, you define your infrastructure. And in this case, we've actually defined our tenants. So we've actually gone in and said, okay, dev has an Acme tenant, and we've defined our base apps. So we defined that we've defined our base apps. This is order processing, for example, and this is nothing special. I'm just deploying a Helm chart here. What it's deploying isn't important. It's an order processing piece, right? But we've defined that in this customization that when Acme gets deployed, it will take this order processing release and it will create a Acme version of order processing. And obviously all the settings and stuff could be extended to this as well. But essentially what it means is that we have now defined Acme, right, as a new customer, and we've defined what happens when Acme gets launched. And this will then, and we can define kind of a base template for that under apps. So we have all these definitions of a tenant. And so all this complexity of, all this special stuff now has to happen when you spin up Acme or a tenant. We can define what a tenant looks like. And then we can also say, okay, spin up all of these for Acme. And that also means if we want to offboard Acme, we lose Acme as a customer or whatever may be happening, all we need to do is delete Acme and all of its resources are all cleaned up, right? So it's a kind of an ingenious way of doing tenant management, right? So we can define all of our tenants, and all we need to do to onboard a new tenant is essentially copy and paste a folder, rename it, it'll reconcile, and this new tenant will get its own namespace, and this new tenant will look at its base configuration and deploy everything it needs. Or you can even do things like, hey, this tenant gets this version of order processing, and this tenant gets this version of order processing. You can even go to that level of granular detail. But it makes a lot of the complexity around doing that much, much, much simpler, right? And that is all defined with Flux, and it's all defined within your GitOps repo. Now, to kind of wrap this, a couple recommendations that we have to do this. T-shirt size your tenants during provisioning. So cost is a major factor here. So one of the suggestions here is, as you might have noticed there, I had a base template for tenants. You can have a base template for a small tenant, a base template for a medium tenant, so on and so forth. So just like cloud providers do, where they take care of making sure that you can pick the right size for your infrastructure, do the same thing for your own. So right size your services, fewer EventHub partitions, maybe fewer database throughput, or if it's an extra large, they get more. Or even if it's an extra large, they get their own database. You can do a lot of interesting things, all automatic, and you can t-shirt size your tenants and get the best experience you want for those customers. You also might want to consider tools such as Crossplane, which allows us to kind of define our applications in an abstract way. So Crossplane is, you can almost think of a little bit more of a templating piece, right? But Crossplane is a really interesting solution to allow you to kind of better define a tenant. And as opposed to deploying all the individual resources for a tenant and the services, you deploy a tenant, and that tenant CRD knows how to take care of all the details behind the scenes. And the last thing I'll mention here, because we are at time here, is that one of the interesting aspects of challenges is deploying Azure resources. How do you deploy Azure resources from Kubernetes, right? And make this all GitOps friendly. Well, there is an Azure Service Operator, which essentially allows you to define all of your Azure resources in YAML, just like you would define all of your existing services. And you can do interesting things like, now you have a dependency. Hey, this service won't install until this deployment for EventHubs is done. So you can add some interesting dependencies once it becomes Kubernetes-ized, if that's a word. But those operators are available at this link here above, and it allows you to have a very, very streamlined deployment experience for whether it's a Kubernetes resource or it's a cloud resource. And I do have some additional resources. I will share out the slide deck with Alec at the end. There are some different resources I suggest for some of the different topic areas I discussed. And once again, feel free to connect with me on LinkedIn, and I'm on Twitter or X or whatever it's called these days. I have a website where I do some occasional blogging, or reach out to me old school on email. And that is time. 1 minute over there. So I know a lot of information, right, for a short period of time. Hopefully this whetted your appetite to look into a few more things. And if there is some interest in deep dive sessions on any of these topics, happy to come back and go into a lot more detail in any of these areas. So I'll return back to you, Alec.
Yeah. Thank you. Do we have any questions that people want to ask recording? If not, I will momentarily stop the recording if anybody wants to ask an off recording question.